Okay, so we're up to Module 8 of Switching, Routing and Wireless Essentials. So we're looking at SLAAC and DHCP for IP version 6. So basically this chapter is all about dynamic address allocation on IPv6. And so we'll look at how you can get an IPv6 global unicast address. We'll look at SLAAC, which is stateless address allocation, and then there's DHCP, which is basically very similar to DHCP for version 4, and how you'll configure a DHCP v6 server. Okay, so on a router, IPv6 global unicast address is manually configured using the IPv6 command, and so of course much the same. IPv6 address, give it its specify the IP address and then its prefix length. So of course for hosts, you can do that manually as well, but that's by far not very common. Maybe for a server, but not many others. However, manually setting it is of course time consuming and error prone, much the same as IPv4 addressing, probably more so. So therefore most Windows hosts are enabled to dynamically acquire their global unicast address. Okay, so of course we also have linked local addresses. So if automatic IPv6 addressing is selected, the host will use an ICMP message and a router advertisement message to help auto-configure the IPv6 configuration. So the linked local address is automatically created by the host when it boots and the Ethernet interface is active. The interface did not create global unicast address in the output because the network segment did not have a router provided, and so that's why we just have the FE80 number and no GUA. Okay, note the percentage in the number at the end of the linked local address is the zone ID or scope ID and is used by the operating system to associate the linked local address with a specific interface. And so there is an RFC for DHCP v6, of course. Alright, so by default, an IPv6 enabled router periodically sends router advertisements, which simplifies how a host can dynamically create or acquire its IPv6 configuration. A host can dynamically be assigned a GUA using stateless and stateful services. So stateless, of course, means you're using SLAAC, which of course uses the router solicitation and advertising messages, or you can add to it with extra information from a DHCP server, a stateless one. So you can actually have one DHCP server set up. Don't need to set up the scopes for everything because the host will figure out their own IP addresses, and then they just get that extra information like DNS server and domain names and things like that. Although host operating systems follow the suggestion of the RA, the actual decision is ultimately up to the host. Then you can have a full stateful DHCP server, which is more like what we had with IPv4, where it actually assigned an address as well as all the other information. So how a client obtains a GUA depends on the settings in the RA message, so the router advertisement. And so there's basically 3 options for the settings inside the RA message. So there's the A flag, which is auto configuration, and that's the default setting, and basically which means that just the router will advertise what network it belongs to, and that is it. With the O flag, it still does the stateless thing, but it says if you send out a DHCP request, you can then get other information, so hence the O flag. And so that's when you would have the DNS server and domain name and things like that. The M flag means managed, and that basically says the router says I will not give you any information. That's up to a DHCP server, so send a DHCP request. And so basically this steers the host what way to go for its address assignment. All right, so the stateless route. Not every network has access to a DHCP v6 server, but every device on an IPv6 network needs a GUA. The SLAAC method enables hosts to create their own unique IPv6 global unicast addresses without the services of a DHCP server. So SLAAC is stateless service, which means there is no server that maintains network address information to know which IPv6 addresses are being used and which ones are available. SLAAC sends periodic router advertisement messages every 200 seconds, providing addressing and other configuration information for hosts to auto-configure their IPv6 address. When a host boots, it can send out a router solicitation message so that it will get an RA when it needs it, as opposed to every 200 seconds. And so SLAAC can be completely stateless, or you can get that other information from a DHCP server. Okay, so how do we enable SLAAC? And so basically, of course, you need to have a router with an address. And so you can set a link local address as well. And we have the global unicast address as well. IPv6 all nodes group, of course, is that multicast address there. R1 is configured to join the all IPv6 multicast group and start sending RA messages containing address configuration information to hosts using SLAAC. So you need to actually do IPv6 unicast routing for it to do this. That actually makes the router an IPv6 router, and that's what starts the RA messages. Okay, the IPv6 all routers group responds to the multicast address FF02::2, and so that only routers listen to that. And so that's actually how you connect to a router. So if you do show IPv6 interface command, it verifies what it's listening for. R1 will now begin to send RA messages every 200 seconds to the all nodes address. So basically, in the router advertisement message, there are flags basically for A, O, and M. Of course, they're the different modes. And so only one of those will be set. And so A means completely automatic. And so that A equals 1 informs the client to use an IPv6 GUA prefix and the RA and dynamically create its own interface ID. So the O and the M would be equal to 0. And so basically from there, that's the only information you're going to get. The ipconfig Windows command confirms that PC1 has generated its GUA. And so here it is there. And of course, it still links, it shows your link local address. Now the router solicitation message. So a router sends an RA message every 200 seconds or when it receives an RS message from a host. So IPv6 enabled hosts wishing to obtain IPv6 information send an RS message to the all routers multicast address. The figure illustrates how a host initiates the SLAAC method. And so in this case, PC1 is just booted, sends its router solicitation message, and then the router replies with its router advertisement message. But it doesn't reply as a unicast to that particular host. It actually replies again as a multicast, just so that all hosts will see it. All right, so using SLAAC, a host acquires its 64-bit subnet information from the router and must generate the remainder of the 64-bit interface identifier, or the host section. Now, there's two major methods. One is a randomly generated number, and so Windows 10 uses that method. Or there's EUI64, which basically means it grabs the 48-bit MAC address from its NIC, and then basically jams 16 more bits in the middle, which of course makes it add up to 64. And normally those bits are FFFE, And so basically from there, that should be a unique number if it's using a unique MAC address. So Windows, Linux, and Mac OS allow for the user to then modify the generation of the interface ID to be either randomly generated or use EUI64. Now, of course, because the host generates its own interface ID or host section, there is an optional process of called what often is called DAD, or duplicate address detection. So basically, once it's decided on its interface ID, it will then actually send out a neighbor solicitation message with its own address as the destination. And so from there, if no other devices respond with a neighbor advertisement message, and so this is basically equivalent to ARP from the old IPv4, if no neighbors respond to that, no one else is using that address, and so it's free to use. So that's basically what it is. So if a neighbor advertisement is received by the host, then the address is not unique, and the host must generate a new interface ID to use. And so often it'll just modify those 4 characters in the middle of the, if it's EUI64, it'll actually just modify those 4 characters that it's jammed in the middle. No, DAD is not required because 64-bit interface ID provides 18 quintillion possibilities. Therefore, the chance of a duplicate address is remote. However, the IETF recommends that DAD is used. Therefore, most operating systems perform DAD on all IPv6 unicast addresses, regardless of how the address is configured. Okay, so DHCP version 6. So stateful DHCP does not require SLAAC, while stateless DHCP does. So regardless, when an RA indicates to use DHCP v6 or stateful DHCP v6, basically the process starts out the same. The host sends a router solicitation message. The router responds with an RA message. Now that RA message will either be other information or managed. I think we're talking about other information at the moment. And then basically from there, the other says, well, you need to send a DHCP request. Or the first message is now called a solicit. So DHCP solicit, which of course they respond with an advertise, and then it's a request, and then it's a reply. So server to client DHCP messages use UDP port 546, while client to server messages use port 547. Okay, so with the stateless DHCP operation, if an RA indicates the stateless DHCP method, the host uses the information from the RA for its addressing, but then contacts the DHCP server for extra or other information. Note that the server only provides configuration parameters for clients and does not maintain a list of IPv6 address bindings. So, for example, PC1 receives a stateless RA message containing the the IPv6 prefix of the network it belongs to, and the flag set to 1 informing the host to use SLAAC, and the O flag set to 1 informing the host to seek that additional information. Of course, the M flag would be 0. PC1 sends the DHCP solicit message and then gets that extra information using the process we looked at previously. Okay, so how do we get that to happen? So you have to modify the RA message, router advertisement message. And so basically in the interface mode, you do IPv6 neighbor discovery, other config flag. And so that will change that flag in the RA packets that it sends. So the highlighted output confirms the RA will tell receiving host to use stateless auto configuration. So the A flag is 1, and contact the DHCP server for other information, which of course is the O flag. Note that it can use no IPv6 and ND other config flag to reset the interface back to default. So here you see the show IP interface. Host use stateless auto-config for addressing. Host use DHCP for other configuration. So if an array indicates the stateful DHCP method, the host contacts a DHCP server for all configuration information. The DHCP v6 server is stateful and maintains a list of IPv6 address bindings. For example, PC1 receives a stateful array message containing the network prefix and length. The A flag set to 0. The O flag set to 0 as well. And so the M flag set to 1. So we're not using autonomous, we're not using other information, we're using fully managed. And so basically, so you'll send a router solicit, the router advertisement will come back saying, I'm not going to give you anything, you need to send a DHCP request. And so then the host will start with the DHCP solicit. And so the way that we do that is by doing IPv6 neighbor discovery managed config flag. And so that changes the RA again. And so as you can see in the information here, it says the host used DHCP to obtain routable addresses. And so that DHCP server actually manages the addressing. All right, so how do we configure a DHCP v6 server? So Cisco iOS routers are powerful devices. In smaller networks, you do not have to separate devices that have a DHCP server client and relay agent. The Cisco iOS router can be configured to provide the DHCP version 6 servers. Specifically, it can be configured to be one of the following: a DHCP server, a DHCP client, or a relay agent. So we've spoken about those roles, of course, in the previous chapter. Much the same. So the stateless DHCP server option requires that the router advertise the IPv6 addressing information in the RA message. So of course, to get that to happen, you need to have IPv6 unicast routing. Then you need to define an IPv6 DHCP pool and then give it a name. And then, as I said before, typically the information you'd give would be a DNS server address and a domain name. You then need to bind the interface to the pool using the IP DHCP server pool name command. And of course, you need to make sure that the flag is set to the O flag is set to 1. Verify the hosts have received the addressing information from the ipconfig/all command. All right. So configure a stateless client. Well, that's not tough. Oh, sorry, the router is a stateless client, sorry. So again, you still need IPv6 unicast routing. You need to then configure the client router to create a link local address. The IPv6 link local address is created on the router interface when global unicast information is configured, or without a GUA, you can use the IPv6 enable command. And so if you want your router to use SLAAC, you can do IPv6 address autoconfig. Again, instead of the IP manually setting the address, and that should actually get the job done. And so verify that the client router is assigned a GUA using the show IPv6 interface brief. And so that's basically it. So then how do you make a stateful DHCP server with a router? And so with this option, it requires the IPv6 enabled router tells the host to contact the DHCP server to obtain all necessary IPv6 network addressing information. So again, you need to do IPv6 unicast routing. You need to create a pool. And then, of course, with that pool, you need to have the options like address prefix command, domain name, DHCP server address, and more. Bind the interface to the pool using the DHCP pool name command. Of course, you need to make sure the M flag is set to 1. And you can do the IPv6 ND prefix default no autoconfig command to inform the client not to use SLAAC. Verify the hosts have received IPv6 addressing again. So that's pretty much the job. Okay, so of course for a client, a router also can be a client. And so again, of course, you need to have IPv6 unicast routing. And so we had auto-config before, but now we do IPv6 address DHCP. Of course, if you want the link local address to come up beforehand, which is normally a good idea, IPv6 enable does that. So just a slightly different to the having it auto-config. Okay, so you can do show IPv6 DHCP pool, and it will actually show the information that you've got. And so this is a stateful pool, and so it's got the addressing there. And so, of course, show IPv6 DHCP binding actually shows you which client has which addresses. Okay, so last thing we haven't spoken about yet is a relay agent. So we did helper address last chapter. Well, they've actually changed the command basically for IPv6. They've done a lot of that. So and so here, of course, we've got a client that needs to get a DHCP information, but the server is actually this one here. And so, of course, the client sends out a multicast. The multicast won't be forwarded. And so with this relay agent, basically it converts that multicast into a unicast to that server. So the command is IPv6 DHCP relay destination and then the address of the router, which of course, if you look at this and this information, that's where we are. And so, of course, you need to do it on this interface here because this is the one that's going to see your DHCP solicit messages. And so you can also check that it's working. So DHCP interface will tell you it's in relay mode. And then on the different route, you can then see that the bindings have happened. Okay, so that's the end of the chapter. So on a router, an IPv6 unicast address is manually configured using the IPv6 command, IPv6 address command, and of course you specify the address and prefix length. When automatic IPv6 addressing is selected, the host will attempt to automatically obtain and configure an IPv6 address information on the interface. The link local address is automatically created by the host when it boots and the Ethernet interface is active. The decision of how a client will obtain its global unicast address depends on the settings of the ARA message. So, of course, we've got auto configuration, we've got other extra information, or we've got the managed options. The SLAAC method enables hosts to create their own unique IPv6 address without services of a DHCP server. SLAAC, which is stateless, uses the router advertisement messages to provide addressing and other configuration information that will normally be provided by a DHCP server. Can be deployed as SLAAC only or SLAAC with DHCP. The SLAAC only method is enabled by default when IPv6 unicasting routing is configured. To enable the sending of RA messages, the router must have that command entered, and you can use the show IPv6 interface command to verify that it's working. All enabled Ethernet interfaces with an IPv6 GUA configured will start sending RA messages with the A flag set to 1 and the O and M flag set to 0 by default. So A, of course, means do the SLAAC method. O, of course, means other information, and M means managed. Router sends RA messages every 200 seconds. However, we'll send one when it gets a router solicitation message as well. So using SLAAC, a host typically acquires its IPv6 information from the router RA, however, must generate the remainder of its 64-bit interface ID either by using randomly generated numbers or EUI. So the DAD process is normally used when that process has been done, which of course DAD stands for duplicate address detection. So it basically sends out a neighbor solicitation with its own message, with its own address as the target. If no one replies, no one else is using it, and so it will keep using it. The host begins the DHCP server client-server communications after stateless DHCP or stateful DHCP is indicated by the router advertising message. And so DHCP v6 uses port 546 and 547. The stateless DHCP option informs the client to use the information from the RA, but get additional information from the DHCP server. And so that's called stateless DHCP because you can often have that will respond to multiple subnets. And so you need to, of course, set the flag to be correct in the RA message by using the ND other config flag. In stateful DHCP, the RA message tells the client to obtain all addressing information from the stateful DHCP server, except the default gateway address, which is, of course, the source from the RA. It's called stateful because the DHCP server maintains the IPv6 state information. And so you need to do the managed config flag for that to work. So Cisco iOS router can be figured to provide server services as one of the following three types: as a DHCP server, as a DHCP client, and as a relay agent. A router can also be a DHCP v6 client and get an IPv6 configuration from a DHCP server. The stateful DHCP server option requires the IPv6 enabled router tells the host to contact the DHCP server to acquire all required information. For a client router to be a DHCP v6 router, it needs to have an IPv6 unicast routing enabled and the IPv6 link local address to send and receive those messages. Use the show IPv6 DHCP pool and DHCP binding commands to have a look at how that's operating. And if the DHCP version 6 server is located on a different network than the client, then the IPv6 router can be configured as a DHCP relay agent, and so the command is IPv6 DHCP relay destination, and then you give the IPv6 address of the server. This command is configured on the interface facing the clients and specifies the server address and egress interface to reach the server. The egress interface is only required when the next hop address is a link local. Verify again by doing show IPv6 DHCP interface and binding. Okay, so there's the logo. That's pretty much it. That's chapter 8 done. We've got one more to go. So that's your first hop router redundancy protocols. All right, see you next time.